All right, last week we learned the basics of binary. We're going to practice it a little bit right now. It's a fundamental in computer science to become comfortable with binary. So in base 10, you know how to count, right? You count 1, 2, 3, 4, 5, 6, 7, 8, 9, and then 10, 11, so 12, 13, 14, 15, 16, 19, 20, and so on. What you do is you go through your first set of digits, and then when you go through all the digits, you add another digit, and then you increment that digit and so on. So in binary, it works the same way. You go 1, and then 1, 0, and then 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, 1, 0, 0, 0, and so on. Since you only have two different values for every digit, the width of your number is going to get big really fast. And last week, you learned how to convert back and forth between binary and decimal. And so you know, for example, that this is equal to 2 to the second plus 2 to the first plus 2 to the 0, which is 4 plus 2 plus 1, which is equal to 7. And so if we count 1, 2, 3, 4, 5, 6, 7, that's another way to get to the value 7. This is the type of thing that when it becomes second nature for you, it'll show that you've had a good, you've built some good fundamentals of how to deal with these binary numbers. Okay, so that's counting. So now let's take it a step further and let's talk about combinations. If I have 3 bits, that means I have 3 pieces of information that each can be a 0 or a 1. How many different combinations do I have? Well, we can draw them out, right? And we can draw them out. We can just kind of pick. We can just kind of figure out which ones we haven't covered yet. And eventually, you should come up with 8 different combinations. I did this in a very ad hoc way. If I just started with 0 and I counted, just like I just showed you a moment ago, I come up with the same 8 combinations, but I come up with them in order. So 3 bits gives us 2 to the 3, or 2 to the 3, depending on how we want to draw it. 8 combinations, which gives us the value 0 through 7. We almost always start counting from zeros when we talk about computer science. So if I want to count 8 times, I go from 0 to 7 usually. Okay, so now let's take that a step further, right? If I have 8 bits, how many combinations do I have? 2 to the 8. If I have 32 bits, how many combinations do I have? 2 to the 32. In order to calculate what some of these bigger numbers are, you can do it manually, right? Or you can recognize that you can use kind of some math with exponents. So let's go through that here in a moment here. So now, if I have 2 to the 5th, that's equal to 2 times 2 times 2 times 2 times 2. That's equal to 2 to the 4th. So 2 to the 5th is equal to 2 to the 4th times 2. In other words, 2 to the 5th is 2 to the 4th doubled, right? Which is equal to 2 to the 3rd doubled and then doubled again, right? In other words, each time I increase my exponent by 1, I'm doubling the value. This is the power of the binary system, is that I can double, and doubling gets numbers big very, very quickly. And so the general purpose of this math that I'm describing is 2 to the x plus y is equal to 2 to the x times 2 to the y. So now for some bigger examples, 2 to the 10. I know what this number is. I know it happens to be 1,024. But the way that you would calculate this is that you can basically go 2 to the 4 plus 2 to the 4 plus 2 to the 2. That's 4 plus 4 plus 2 is equal to 10, which is equal to 16 times 16 times 4, right? This is 2 to the 4, this is 2 to the 4, and this is 2 to the second. And so this might be a faster way for you to get there. 16 times 16 is 256. 256 times 4. You can think 250 times 4 is 1,000. So 256 times 4, 1,024. If this is confusing, rewind this and listen to this again, because this is really a fundamental piece of what we want to do, is this whole concept of combinations or encodings. If I have 16 bits to represent a bunch of combinations, how many combinations can I represent? 2 to the 16. If I have 4 bits, how many combinations can I represent? 2 to the 4. And I don't expect you to be able to tell me what this number is off the top of your head. I do kind of expect you to be able to tell me what that number is off the top of your head. 2 to the 4 is 16. And you should be able to calculate up to these bigger numbers. If you know that 2 to the 10 is 1,024, then you can approximate 2 to the 20 as 1 million, right? 1,000 times 1,000 is 1 million. And then 2 to the 30 is going to equal to 1 billion, which is 1 million times 1,000. And so you can kind of get fluent and kind of being able to bounce around with some of these calculations. Okay, I do have a question on the lab, I believe, that basically says, you know, how many memory locations can be represented by, I think it's a 10-bit field or maybe it's a 12-bit field, right? This is exactly what we just did, right? If I have a block of memory and that's memory 1, that's memory 2, that's memory 3, and that's memory n minus 1. If I have a 10-bit field, then it can represent 2 to the 10 memory locations. And that would be 0 up to 1,023. We have to be able to go in the other direction as well, right? So if I have a memory bank of 1,024 cells, I might ask you, what size bit pattern or what size field do you need to be able to cover all of those, right? So this is going in the other direction. In other words, what's 2 to the question mark is equal to x if I give you x. And just some quick examples of that. 2 to the question mark is equal to 64. 2 to the question mark is equal to 256. 2 to the question mark is equal to 4 billion, approximately. This last one would be 32. 2 to the 64, or 2 to the 6th is equal to 64. And 2 to the 8th would be 256 because I double 64 and then I double it again. So I go 6 to 7 to 8. Again, if this is confusing, the best way to become fluent in this is to just do it over and over a few times. And so you can practice doing exactly what I'm doing, or you can rewind it and watch it again and rewind it and watch it again. Now, I might ask a slightly trickier version of the same problem and say, let's say that I have a memory bank that has 2,912 cells in it. I might ask, how many bits do I need to be able to cover all of those? There is no value that I can put in here to make 2 to that power equal exactly 2,912. So what I have to do is I have to make this really greater than or equal to. I got to have this number be big enough so that I can uniquely cover every one of these cells, but I may have a few more spaces than needed, right? So for example, if I have only 3 things that I want to cover, so if I have 3 different cells that I want to cover, I can use 0, 0, 0, 1, and 1, 0 to cover those 3, but then I have 1, 1, which basically I don't need. And so in order to calculate this answer to this, you just got to find the right number where 2 to that power is greater than or equal to 2912. And if we know that 2 to the power of 10 is equal to 1024, then 2 to the power of 11 is approximately 2000. 2 to the power of 12 is approximately 4000. So we know that this answer will be 12. And you don't have to do the math exactly here, because we know that once we hit, we know that we don't have to hit this exactly, so we can kind of abstract away. Exactly, this is 4096, and exactly this is 2048. And if you're like me, at some point you'll have 2 to the 20th all the way up, 2 to the 0 all the way up to 2 to the 20th memorized, because you've just done it so much that you know what they are.
Why are they always making
The last thing to cover as part of this topic is to talk about big memory. And big memory is important because we deal with it every day, right? If you pull out a thumb drive or your iPhone, or you look at a solid state hard drive, you're going to see big memories. So we'll start with a kilobyte, often abbreviated that way, kilobyte. Now we know from our metric system that kilo is 1,000, right? So a kilometer is 1,000 meters, or a kilogram is 1,000 grams. It gets tricky in computer science, because if you were to go find me and 9 other of my colleagues, or even ask me on 2 different days, I might give you 2 answers. I might say that a kilobyte is 1,000 bytes, or I might say that it's 1,024 bytes. Because kilo, this is the power of 2 that's closest to 1,000. And so the question is, which one of these is correct? And the answer is, it depends. Technically, per definition, this is correct, 1,000. However, you will see very, very commonly the kind of this computer science version of kilo being used. The same thing is true for a megabyte. So 1 kilobyte so 1 megabyte would be 1 kilobyte times 1 kilobyte, right? Which could be either 1,024 times 1,024 or 1 million, which is 1,000 times 1,000. Clearly, if you're trying to be precise, dealing with a round number like a million is easier. However, remember, computers deal with powers of 2. So this number is a much more natural value for a computer to deal with than this number. And in fact, 1,024 times 1,024 is just going to be a binary number that looks like that. So in other words, in base 2, it's a nice simple looking number, just like this is a simple base number in base 10. Okay, so I wanted to pause on this just really quickly, because in assignments and labs, I might say, I have these story problems in the labs, and I might say, how many songs can you fit on a 256 megabyte, iPod shuffle? And so if you're trying to be precise, you have to tell me that you think of that you're thinking of megabytes as as this or this, and whichever one you pick, unless I specify, whichever one you pick will be the right answer. Okay, so any questions to this, please follow up on the discussion board and we can add to it.